Right. So we just heard about upcoming quantum language designed for formal verification. Now let's talk about existing high-level quantum language and its formalization. So Q# is a quantum domain-specific language from Microsoft that has been in development since 2017. And like most other industrial languages, it does not have a precise formal specification. So in this work, we are trying to provide it a formal definition and also proposing some extensions that will help improve its type system more. So this is ongoing work with my collaborators, Sarah Marshall, Kesha Haitala, and Robert Rand. And in the rest of this talk, I'll give a little bit of background on Q#, introduce our core calculus called lambda Q#, through which we model the Q# programming language, and then provide an extension of its type system that lets us statically enforce the no-cloning theorem. So before we go there, the question is, why do we even need to specify languages formally? Right. So in classical literature, we have known for a lot of time that sound language design principles lead to programming languages in which it's easier to write, to compose, and maintain programs. And we take inspiration from existing previous works such as standard ML, Java, Go, JavaScript, and Rust that have shown that, first of all, this formalization can be done, and also that doing that has large benefits, such as in evaluation of the language. So for example, if you think of generic support in Java, which came in Java 5, a lot of it was supported by academic literature and research. And most recently, the Go programming language probably will get support for generic soon because it has been proposed through the Featherweight Go project. Further, in our case, so one of the principal designers of Q#, Bettina Heim's thesis states the design principle 5, that Q# is a living body of work that will grow and evolve over time. So our work is sort of aligned with this design principle to help it evolve. Now let's talk a little bit about Q#. As I said, it was announced in 2017. And really, it's a functional programming language in the skin of imperative style language. There's a really nice talk and blog post by John Azaria from 2018 that discusses this history of how Q# came to be from previous projects from Microsoft, such as Liquid and then Solid, and which were all written in F#. A little bit more about Q#. You can run it as a standalone command line application. The programs that you write in that, you can run them in Jupyter notebooks. And also you can interoperate those programs with classical host languages such as Python or .NET languages like F# and C#. Other thing that sort of makes Q# stand out is that it has an extensive library of quantum-specific support code, such as for chemistry applications, numerics, and quantum machine learning. And there's a dedicated team working on the Q# compiler, and they also maintain a large learning resource repository, something they call quantum katas. Talking a little bit about the features of the language, it takes this usual QROM model for how it treats quantum computation, where a quantum computer is a coprocessor. And the specific view that Q# designers took was that each computation is by side effects. So it's a little bit like Haskell, where you can write imperative code, specifically side effectful imperative code, and it's considered as a monadic sequence of instructions. Another unique thing is that it maintains a clean separation between classical and quantum parts of the code. So they distinguish two kinds of callables, functions, which are pure classical functions, and operations, which contain all the quantum effectful code. Then the language supports metaprogramming using adjoint and control operations, which can be applied to existing operations. Some of these can be auto-generated as well by the compiler. And then it has first-class callables, using which you can do higher order programming. And one thing that I really like is that it supports immutability by default. So here's a sample program in Q# to write teleportation. As you can see, the keyword here is operation, so it's a quantum callable. It takes 2 qubits as input and returns unit as output. So this is where you're seeing side effectful nature of the language. And I just want to highlight that the use keyword is used to allocate a new qubit. So this instruction allocates a single new qubit. And the rest of the code is what you'll expect. You create entangled state, send the message, measure it out, and do the decoding. So what do we mean when we talk about doing formal specification for a language? So here's a recipe, which is motivated by the work that was done for standard ML. In fact, the title of our paper is inspired from that work as well. So what we can do is we can define a well-behaved internal language, also called a core language. In our case, we are calling it lambda-Q#. To connect this language from the external or surface language, you need to define an elaboration relation between the two. And once you have the internal language well defined, you can start talking about the semantics and write statics and dynamics using that language. And statics just means the type system, which will rule out meaningless programs. And dynamics means at a high level, what do the programs mean? It could be an operational semantics, denotational semantics, sometimes it could be categorical. So once you have all these defined, you can start proving meta theorems such as type preservation or safety. Now, another thing you can do once you have this formalization done and read the benefits is that you can study if you extend the language somehow, what happens, whether that works well with the rest of the language or not. So we'll show an example today of that. So here is our part of our core calculus, lambda-Q#. It's a simply typed lambda calculus, but with some differences, and I'll highlight those. So what you're seeing on the left is the formal syntax for expressions and then types below. On the right, there is a little bit more convenient syntax in which programs are easy to write. So it will be highlighted in blue. And on the further right, there's some comments. So let's talk about these orange colored symbols called qubits. So these are opaque symbols. These are special. They're not visible in the surface Q# language. So we have introduced these for meta-theoretic reasons. There are the usual lead bindings. You can do abstraction, application, and there's an encapsulation command, which kind of separates out or encapsulates the effectful code. And we'll see more about this in the next slide. There is this reference here called a qubit reference, which is actually what corresponds to qubits in Q#. We'll see how this looks like later. Then the types are pretty much what you will expect. There's a qubit type, which corresponds to those orange symbols. There's a qref type. And one would ask, why didn't we just create a reference type? The reason is that Q# does not really have a notion of references. It only has this implicit treatment of qubits as references. So we just instantiated the reference type to be a qubit reference type. Right? Then there are arrows, command encapsulation type, which basically types the return value of the command, and this unit. And this green symbol kappa is something I'll talk about in a later slide. Moving on to commands. Since it's a monadic language, you have return and bind as usual, and there are some quantum specific commands. So first of all, you can declare a new qubit, obviously something you need in Q#. So what this does, it creates a new qubit symbol, and its scope is very clear that it's within the scope of this command. So it has the lifetime of this qubit is limited to the lexical scope of this declaration command. Then there are two operations that we support currently. One is called gate app ref, or R means ref here, and similarly a control app ref. So gate application applies a single qubit unitary gate U to an expression E, which will ultimately resolve to a qubit reference if it is correctly typed. And similarly, control U applies the operation U to E2, controlled by E1. So the takeaways from this language so far is that, one, it maintains a separation between the classical and quantum parts of the language, just like Q# does. And importantly, the qubit type that we see in the surface Q# language, it corresponds to the qref type. of qubit references, not the orange qubit symbols. So let's see an example. Here you're seeing a tiny example written in Q# on the left and lambda Q# on the right. So what we're doing is creating a new qubit, right? So Q1 will get a qubit, whatever that means in Q#. Then you're creating a new binding for that qubit, call it Q2, and then applying C0. So this is obviously incorrect because you're applying C0 to a qubit as its control and target, which is functionally equivalent to cloning the qubit, right? In lambda Q#, this is made a little more explicit, where you see that we created this new qubit symbol, created one binding, which is reference to this qubit, and then another copy of the reference. So Q1 and Q2 are of same type. It's completely clear. And then apply the same thing. So the problem is that Q# currently cannot statically prevent this issue. And question is, can we do better in our language? And yes, so let's see how. So we'll step through the code on the right in the previous slide and see the typing context evolve. So here, first of all, we are creating a new qubit, Q. So obviously, so this turnstile symbol is separating the typing context from the current expression to be evaluated. So we get a new binding Q, whose type is qubit, in which we will evaluate this expression, which is a lead binding. Right, so Q1 is the new binding to be created, and we are taking a reference up to this qubit. So something strange happens. So in the new typing context, you get Q1, which is a new binding, and we see that it's correctly typed as a QREF, and we see that green colored kappa symbol appear again, kappa 1 here. Right, so we call this a lifetime variable, and on the right, you see that the type of Q has changed as well, which is something we'll see does something interesting. So the type has changed in this way. We have appended a dagger and a kappa 1 to it. So the way to think of this new type is that the type of Q, which is qubit, is blocked until the end of this lifetime kappa 1. So this dagger can be thought of as a, when the kappa 1 gets killed, then the qubit's type can be recovered, right? So now that you have this typing context, when you create a new binding for this Q1, you will get something similar will happen, where a new binding is created with a different lifetime kappa 2, which is intuitively smaller than the lifetime we had for the previous qubit. And then the type of Q1 again gets changed to dagger kappa 2. That is, its type is blocked. So now when we try to type this expression, controlled X, in this typing context, it leads to a type error. And the reason is that controlled X intuitively requires 2 qubits, but only the type of Q2 is correct in this context, while Q1's type is blocked. So this is how we can easily prevent cloning in this simple example, right? More formally, what I showed you is exactly what happens in Rust when you think of borrowing and reborrowing for mutable references. So I'm only showing typing rules which are relevant for reborrowing. That is the second left example. So here's a coercion rule. So we have a lifetime context called L, which keeps relations such as kappa 1 is included in, or kappa prime is included in kappa. So it keeps track of lifetime inclusion relationships. And what we are seeing is that given a context gamma with a binding, along with a binding X, which is QREF with a certain lifetime kappa, you can split that binding into 2 such that gamma remains the same. And you can create a new binding with a new lifetime where, and change the type of the previous binding X to a blocked type. This is exactly what we saw in the previous slide, just in a more formal setting. And now you can see the type of the let expression, which includes gammas and lifetimes. And here in the top, you're seeing when during the creation of the new binding X, the portion of the typing context gamma 1 changes to gamma 2. And then that helps you type the rest of the expression. And for completeness sake, I've shown the type of control APR here as well. So this sort of shows you the current state of the formalization. I mean, since the submission of this paper, we have done a little more work and are doing more. So we have included generalized product in some types in the language. So you can start encoding Booleans, polys, and result types from the surface language. We have also included mutable bindings and arrays, working on measurement and polymorphism. Since we have a notion of lifetimes in this lambda QSHA, we need to also consider lifetime polymorphism. We need to also treat metaprogramming constructs such as adjoint and controlled more explicitly. Plus, we have started working on the mechanization of the meta theory. And for that, the main tools are primarily, you need some sort of a logical framework. In our case, we have ended up choosing Coq along with some tools such as ORT and LNGen, which will help us automate a lot of meta theory in our locally named list representation. So future steps include formalizing the elaboration from the surface language to lambda QSHA. And also more recently, newer generation intermediate languages have been proposed for QSHA, including one from Microsoft called QIR. So we hope to create a tool chain where we can provide semantics preserving compilation from QSHA to some of these languages. And also some of these are LLVM based, such as QMLIR and QIR. So there is a possibility in the long term to integrate with existing tools such as Vellum, which is a verified LLVM project from UPenn, which could help us extend the verification toolchain. Yeah, this is all. And so in this talk, I presented you our ongoing work on formal specification of the QSHA programming language. In its current state, lambda QSHA maintains a separation between classical and effectful quantum sublanguages. We treat underlying qubits more explicitly to be able to control interference between references. We have also proposed a solution for statically preventing cloning in following lambda Rust from the Rustwell project. And there's a lot of exciting future work to be done. And we are excited about that. And I'm happy to take questions now.